Welcome listeners to the third part of the discussion on crystallography, and I am Dr. Shandeep Banerjee, a faculty member in the Department of Geology, Banaras Hindu University, Varanasi. So, earlier in the first two parts of discussion on crystallography, we have looked into crystal properties, crystal symmetry, and also we have understood that how crystal symmetry is extremely useful, and this is what is considered under geometrical crystallography. So, the understanding of symmetry is extremely important to interpret any kind of crystal structure. And talking about now about crystal system in detail, we will plunge into that, but before that we need to have an idea in continuation with symmetry theory, that when an array of points are connected by the same translation element, like we have seen in case of the arrangement of the motifs in a chain, the same translation element, then the points are nothing but they are the lattice points. So, you can see that this translation is continuously generating lattice points one by one with in a particular direction with the same magnitude. Then if I now think of several lattice points like this, which is also referred to as a lattice net, when several lattice points are arranged over a space and it defines a net like structure, then it is referred to as a lattice net. So, in that again, if I think about the translation, then in this direction from left to right, I can say that you have this translation. Similarly, for this array of lattice point also, the translation will be same, because now you are in a two-dimensional lattice net. So, in a particular direction, your magnitude of translation will be always and always equal. So, you have this translation here. I can write, for example, here as this one as T1, this one also as T1. Then if I go to the second or if I go in a different direction, I can also say that the translation along this particular direction is always T2. So, now you have a set of 2 T1 and 2 T2, which is defining the position of this 4 lattice point in the lattice net. So, this rhombic kind of you can say group of translation defining this rhombic geometry is what we refer to as the unit cell. Again, unit cell is the basic building block of any crystal, and each and every you can say lattice points are arranged with or the arrangement of the lattice points that are related with some kind of translation in a particular direction will define the unit cell. So, based on that idea, same thing I can do in a pattern, like if I take this one again as the T1 translation, also this one, because they are again in the same direction, so it has to be T1. But I can take a different set like this one and this one, which is now for example T3, this is also T3. So, now I can also have a different kind of a unit cell within the same lattice net with the same arrangement of lattice point, but now your choice of translation is different. So, a combination of T1 and T3 translation is now giving you a different kind of an unit cell. So, the lengths of the various crystallographic axes of a crystal are defined on the basis of this basic building block, that is your unit cell. Now, depending on the length of the axis and also the angle between in the axis, crystals are, you can say, subdivided or classified under different crystal systems. So, it is also expressed as the ratio between A, B and C axis, like I was mentioning, A axis, B axis and 3 axis in 3-dimensional reference frame. So, in that case, the first one is your isometric system, where the length of each and individual axis, the unit distance will be exactly same for each and individual axis. So, here you have the length of A axis equal to B axis equal to C axis. That is why it can be expressed as an axial ratio of 1:1:1, which is a character of isometric system. Then the second one, the tetragonal system. Here the unit distance of A or the axial length of A is exactly same as the axial length of B. So, likewise, but it is not same as that of the C. So, C is either a little longer or shorter in comparison to the axial length of A and B. So, that is why it is expressed as 1:1 representing A and B is to C. Again, for orthorhombic crystals or the orthorhombic system, here the axial length of again A, B and C, now they are no longer equal to one another. So, the axial ratio of A will be different. The axial ratio of A, B and C will be expressed as A:1:C. Here remember, generally we consider B as standard unit distance of 1. So, we always express the axial ratio in terms of 1 axial length of B. So, likewise the ratio will be A, which is not equal to 1, is to 1, which is equal to obviously 1 unit of axial length of B, which is again not equal to C. So, it will be expressed as A:1:C, like we get to see in case of sulfur crystal, that your 0.8131 is the axial length of A, is to 1 axial length of your B, and the axial length of C is again 1.9. So, the ratio or if I want to express, I can write A is not equal to B, not equal to C. Again, there are two other crystal systems or types of crystal, monoclinic crystals and triclinic crystals. In that, again, the axial lengths are not equal to one another. So, the axial ratio for these two crystals, monoclinic and triclinic crystals, will be also A:1:C. For the final one or the final two, hexagonal and trigonal one, one of the best example of hexagonal crystal is quartz as well as beryl. So, for that there are three now, your three horizontal axes, that is A1, A2 and A3, and the vertical one is your C axis. So, now the axial length of A1 is exactly equal to A2 and exactly equal to A3, but it is different from that of the C axis. So, the axial ratio can be written as 1:1:1:C, or simply as all the horizontal axes have exactly same axial length, you can also simply denote it as 1:C. But apart from the axial length, to quantify or to segregate these different crystal systems, apart from the length, you also need the axial angles, means the angle subtended between each and every axis. So, you have one angle between A and C axis, that is represented as your beta. You have gamma angle, that is the angle between your A and B, and you also have your alpha angle, that is the angle between B and C. So, you have these three angles in between each and individual axis. So, based on this angle, the first one again for cubic system, the alpha is equal to beta angle is equal to your gamma angle, which is also equal to 90 degree. So, I can think in a manner that all the axes A, B, C, they are mutually perpendicular to one another. So, the angle between them is always 90 degree. Similarly, the same thing is applicable for your tetragonal crystal or tetragonal system, where your again alpha, beta and gamma angle are equal to 90 degree. That also means that the three axes are mutually perpendicular to one another. Same thing is again applicable to orthorhombic system or orthorhombic crystal. But here I would like to remind you that though the axial angles for cubic, tetragonal, cubic means isometric as well, cubic, tetragonal and orthorhombic crystal, where the axial angles between them are always 90 degree. Remember, the axial lengths are not same. In case of isometric crystal, the axial lengths are same. In case of tetragonal, the C axis is not same, but A and B are same. In case of orthorhombic, all the three axial lengths are different. But in case of axial angles, in this case cubic or isometric crystal, tetragonal crystal and orthorhombic crystal, all three have same axial angle. So, you can't really differentiate between cubic, tetragonal and orthorhombic based on directly only on on the basis of axial angle. You also have to have an idea about the axial length. Now talking about hexagonal one, for hexagonal, you know, like I mentioned, there are three horizontal axes, A1, A2 and A3, and each of them are at an angle of 120 degree to one another, because these are going to one end to another end, and if I always take the positive end, then in between the positive end of the horizontal axis there will be 120 degree angle. Individually again, if I take the negative ends of the axis, there will be again angle of 120 degree, but if I take a combination of a positive and negative end of the axis, then the angle between them will be 60 degree. But this C will be always vertical in nature, these three horizontal axes, with respect to these three horizontal axes. So this one will be obviously vertical or mutually perpendicular with respect to all these three axes. So and also, like we have seen in case of your axial lengths as well, your C axis will be either greater or less than that of the axial length of A1, A2 and A3, but the axial length of A1, A2 and A3 will be exactly same. Now you have this two kind of crystals or system, your monoclinic system and triclinic one. So the crystals belonging to this system in axial length, like we have seen, they are different. That means the axial ratio will be A:1:C. So definitely that means the axial length of each and individual axis, in case of be it monoclinic crystal, be it triclinic crystal, it will be different. But in case of axial angle, now in case of monoclinic, you have alpha angle is equal to your gamma angle, which are both 90 degree in nature, but the beta angle, that the beta angles means the angle between A and the C axis is not equal to 90 degree. So that means there might be a change in the angle between your C and A. So earlier, in case of your cubic, tetragonal or orthorhombic, even hexagonal, the angle between the vertical axis, that is C, with any horizontal one is always 90 degree. But now in case of monoclinic, you have a tilted angle between, or the angle is no longer equal to 90 degree, specifically the beta angle, which is the angle between C axis and A axis. But in case of triclinic, it is further more complex. None of the angles are now equal to your 90 degree, be it your alpha angle, beta angle or gamma angle. Now none of them are equal to 90 degree. That means all the axes are kind of tilted a little bit. Maybe this one is elevated a bit, maybe this one is a bit tilted, maybe this one is also a bit tilted. So none of the angle, be it your alpha angle, be it your beta angle, be it your beta angle, be it your gamma angle, all these angles are no longer equal to 90 degree. So here also you can distinguish, though the axial ratio of monoclinic and your triclinic, they might look similar, but the axial angles are obviously different. In case of monoclinic, only the beta angle is not equal to 90 degree. In case of triclinic, none of the axial angles are equal to 90 degree. And you also have a rhombohedral one, or the most the most common example of a rhombohedron crystal is like this. Like we have seen for the inversion center of symmetry, where we have inverted the crystal again and again to look at the operation of inversion. Similarly, there is a mineral called calcite, which will give you an exact same appearance like this crystal. So in this case again, you have this three angles, because here the axial lengths, coincidentally the axial lengths, though they are tilted, all the axes are tilted, but the axial lengths are equal, means the axial ratio will be 1:1:1, but the angle between them, obviously as the axial lengths are same, the angle can be also depicted as your same, means alpha. In place of beta also you will say alpha, in place of gamma also you will say alpha, and all these are never equal to 90 degree, but itself they are equal to one another, means alpha is equal to beta is equal to gamma, but they are not equal to 90 degree. But remember, this alpha can be replaced in case of beta as well as gamma. So these are the 7 crystal systems that you can find in the broad study of crystallography, and there are several minerals and crystals, they belong to this individual crystal systems. Talking about now crystal forms, because these are also directly related to the crystal systems. So a crystal form is a set of crystal faces that are related to each other by symmetry. Always remember that if you are looking at crystal, it has to be some kind of symmetry, be it only one symmetry element is present in it, be it all the 4 symmetry elements are present in it. To designate a crystal form which could imply many faces, we use the Miller index like we have seen earlier, and the notation is called a form symbol, like we can look at this one. So if this is 1 1 1, this I is your center of symmetry about which your this face is getting inverted. So as this 1 1 1, I am looking at a 1 1 1 face which is cutting the A, B and C axis at one unit distance. Similarly, the inverted face to it, if I look at the inverted face, so if this is one face, the inverted face will be like this. So in that case, it will cut all the 3 axes A, B, C at negative ends now. So they will be represented as Miller indices of bar 1, bar 1, bar 1. So, and this inversion is taking across this center of symmetry. Now again you have 2 broad kind of simple forms, that is open form and closed form, and as the name suggests, simply closed form is an assemblage of faces which can enclose a volume of space. Similarly, open form, as the name suggests, an open form is one or more crystal faces that do not completely enclose a 3-dimensional space. So there are several forms, but I will only discuss a few of the common forms here. So the first one is a pinacoidal form, which is a 2-facet form made up of 2 parallel faces like we have seen here. So these 2 faces which are parallel to one another with Miller indices like this 1 1 1, and the inverted one is bar 1 bar 1 bar 1. So for these 2 faces we will refer it as pinacoidal faces. Then you have domal faces like this. Domal faces are 2-facet form where the 2 faces are related with a mirror plane or a plane of reflection. So there must be a mirror, that is an symmetry element that should be present between the 2 planes, and if I simply do the reflection, you will get the same plane on one part onto the other part. So simply if I again take, though this is not strictly domal face, but if I think about, or if I take this one, the first one, I can simply think that there are parallel, there are faces like this. If I think of a mirror plane that is going through this like this, only a mirror plane is present. We will also talk about rotation in a bit. So these 2 planes will form, this assemblage of these 2 planes will form a set of domal faces. Then you also have sphenoids. Sphenoids are 2-facet forms where your faces are related with the operation of a rotation, that is specifically here it is a 2-fold rotational axis. If now again I take this as an example, this crystal model, then I can hold it like this. If I look at a face, this smaller one, if I look at this smaller face and if I rotate it about 180 degree, you will get the same face here. So I can say that, be it again, if I also take this one and if I rotate it about this axis through which I am holding the crystal, if I rotate it, you will get exactly the same face. So you are dealing with a 2-fold rotation leading to the occurrence of these 2 faces in the space twice. That is why with a rotation of 180 degree, I am getting the occurrence of the same face twice. That is why it is known as 2-fold rotation. So you can think of these sphenoidal faces like this, which are obviously not parallel faces. They are not parallel, they are inclined faces, but if I rotate it, I will simply get the occurrence of same face again and again with a rotation of 180 degree. So these are what we know, what is known as sphenoid or sphenoidal faces. Then you have prism faces. Now this is the This crystal gives you both prisms and pyramids. I will talk about this now. So, you have these faces which are 3, or there should be 3 or more faces, unless that it might become a domal face. So, you need, so for domal faces you need 2 faces only, but for prism faces you need 3 or more faces. So, here I can think of this particular crystal, and you can see at the middle of the crystal you have these 4 faces which are parallel to one another, which are not intersecting at one end. They are obviously intersecting when they are adjacent to one another, otherwise they are not intersecting, they are moving parallel to one another. In that case, these are referred to as your prism face. Similarly, you have also at the top of this crystal as well as at the bottom of the crystal, you have this inclined planes. Again 4 planes you can see from a different angle as well. These 4 planes, they are intersecting at this vertex like this. So, these 4 planes which are intersecting one another will be treated as pyramidal face. So, this crystal I will say is a assemblage or combination of prism faces and pyramidal faces. Prism faces at the middle, so you have 4 prism faces, and pyramidal faces on the top as well as prism faces at the bottom. So, you have 4 prism faces at the middle, 4 pyramidal faces at the top, 4 pyramidal faces at the bottom. So, likewise you can see that it is a combination of prism and pyramidal faces forming totality. In totality it is a closed form, because it is enclosing some 3 dimensions space within in the faces. So, like this I was mentioning you, so you have your prism faces. So, there are different forms, trigonal prism, diagonal prism, depending on the number of faces you are dealing with, also depending on the rotation axis. Now, if I am say that I am dealing with a prism face, then this prism face has to be related, the main characteristic element of symmetry for this symmetry for these prism faces would be axis of rotation. The axis of rotation could be 3-fold axis when we are dealing with 3 prism faces, it could be 4-fold when we are dealing with 4 prism faces, or it could be also 6-fold depending on if we are dealing with 6 prism faces. So, in that case you will have the occurrence of 6 times of the same face. So, that will give you 6 prism faces which will be related with this axis about which I am holding this crystal, will give you a 6-fold symmetry. Similarly, in case of this pyramidal faces as well, you will get a 4-fold symmetry, because this face is getting repeated 4 times with a rotation of 360 degree. So, the same face is getting repeated 4 times with a rotation of 360 degree. That is why again I can say about the axis through which I am holding this crystal is giving you a 4-fold rotational symmetry. So, you are getting 3-fold rotational symmetry, 4-fold or even 6-fold symmetry, both in case of prism faces as well as pyramidal faces. But do remember, prism faces are parallel faces like this, and pyramidal faces are inclined and intersecting faces that you will find in a crystal, and generally you will find in most of the crystal you will find a combination of that, and they will enclose some 3-dimensional space, and that will ultimately give you in totality a closed form. There are various varieties of this prism face and your pyramidal faces. You can also have general form and special form for specific minerals or specific crystals. So, a general form is a form in particular crystal class that contains faces that intersect all the crystallographic axes at different lengths. Means, so a Miller indices, if I think about now isometric system, then a Miller indices of 1, 2, 3. So, if I convert it back to Weiss parameter, what would happen? The Weiss parameter will be 1, half and 1/3, because ultimately by taking the reciprocals we have been finally been able to find out the Miller indices of 1, 2, 3. So, that means the axial length of isometric crystal, where the axial length is exactly equal, but I am having the intercept of 1/3 at one place, half at one place, 1 at one place. for individual axis. That's why the Miller indices are 1, 2, 3. So that means you are dealing with a face which is cutting all the 3 axes at 3 different length, not the same length, though the individual axial length of an isometric crystal is exactly same, A is equal to B equal to C. But now if I take a face that is having a Miller indices of 1, 1, 1, so the Weiss parameter or the intercept would have been 1, 1, 1. So that means it is cutting the A axis at the same distance where it is cutting the B axis, at the same distance where it is cutting the C axis. So now a Miller indices in case of isometric crystal, the Miller indices of 1, 2, 3 of a face, that will become a general form. The Miller indices of a face with Miller indices 1, 1, 1 will become a special form. So it is just by the virtue of the intercept of the faces with respect to the individual axis. So a general form again is a form in a particular crystal class that contains faces that intersect all crystallographic axes A, B, C at different lengths. If it is cutting at the same length, then definitely it is special form, it is no longer a general form. Now obviously there are, like I was mentioning, there are 7 crystal systems in total, like we have seen, and 32 classes, and every crystal system they possess one normal class. The normal class, which is also known as your holosymmetric class or holohedral class, in that should possess always the highest degree of symmetry in that particular system. So if I am now looking at the normal classes, for starting with the isometric system, if I am talking about the normal class, then the normal class is a mineral that is known as galena, which have a very characteristic cubic shape. So the basic symmetry that should be present in isometric system or for any isometric crystal is the presence of 3-fold rotational symmetry, 4 in number. The other symmetry elements that could be present or that are present in the normal class, if I say, then there should be 9 reflection planes, there should be total 13 rotational axes, and there should be also a center of symmetry that is present in that. Then you have your trigonal system where you have minimum 1 4-fold symmetry. The normal class is zircon. You can also read it from the slide itself, the details. I will only talk about the characteristic symmetry element here. You have orthorhombic system where you need to have minimum 3 2-fold rotational symmetry. The normal class is of barite. Then you have the monoclinic system where minimum you need 1 2-fold rotational symmetry, and the normal class is gypsum. You have hexagonal system. The normal class is again beryl. I also talked about quartz a bit, where the minimum requirement to a crystal to be or belong to your hexagonal system, you need 1 6-fold rotational symmetry. And you also have the trigonal system where you have this is again the calcite, which is the normal class. This is an example of calcite, which should have 1 3-fold rotational symmetry. You can see this face is getting rotated or is occurring thrice with a rotation of 360 degrees. So the same face is getting repeated thrice with a rotation of 360 degree about an axis. So you need minimum 1 3-fold rotational axis in case of a trigonal system. The normal class is again calcite. For triclinic, the normal class is axinite, and the crystal must possess 1 fold axis of symmetry only. You don't need any other kind of symmetry. The 1 fold means with a rotation of 360 degree, one face will only occur once. So you can say that is the minimum symmetry a crystal might possess. So to summarize it in brief, so you have the crystal system for triclinic, 1-fold rotation or an inversion center is necessary. For monoclinic, 1 2-fold rotation, 1 mirror plane or both is necessary. For orthorhombic crystals, 2-fold rotation axis or 2-fold rotation plus mirror planes are necessary. Trigonal, 1 3-fold is the minimum bare requirement. For tetragonal crystal, 1 4-fold rotation is bare requirement. For hexagonal, one 6-fold rotation is bare requirement, and for isometric there should be at least 4 3-fold rotational axes. And this are also, the symmetry are also expressed with the help of a notation, that is Hermann-Morgan symbol or the Hermann-Morgan notation. For example, if you are looking at the barite crystal of orthorhombic system, it is denoted as 2 by em 2 by em 2 by em. That means there are at least 3 exclusive 2-fold rotations, plus there are at least 3 exclusive mirror planes that are present in the crystal. So there are these 3 axes. These 3 axes are acting as your rotation axis. Also there are mirror planes which are along this axis. So before I finish, I would simply like to remind you of the great discovery of X-rays, based on which the crystallography subject has developed very fast since 19th century, and which by Roentgen, who actually discovered the X-rays in the 19th century. Based on the idea of X-rays, the science of crystallography has modified largely. So here I would like to stop with the discussion on crystallography, with 3 parts discussion on the subject of crystallography in the broad series of discussion on fundamentals of geology. Thank you.